Okay guys, so for this video we are going to be going over 2016's AP Calculus AB FRQ number 5. So first let's go ahead and read through the problem. The inside of a funnel of a height is 10 inches and has a circular cross sections as shown in the figure above. At height h, the radius of the funnel is given by this equation where the interval is from 0 to 10. It's a closed interval. The units of r and h are inches. So for A, we have to find the average value of the radius of the funnel. So once you read this, you should immediately identify the equation to find the average value. So if we come down here, we have the average value equation, which is 1 over b minus a times the integral of from a to b of r of h dh. And this is because we want to find the average value of the radius, as it says here, so we are going to use the radius equation that we are given. So now let's go ahead and plug in our variables that we're given. So it's 1 over 10 minus 0 times the integral from 0 to 10 of the radius's equation. And first we want to go ahead and factor out the 1 over 20. That's going to make simplifying and everything a lot easier. So we get 1 over 200 times, after we take the integral, 3h plus 1/3 h cubed, and we still need to plug in the values 0 and 10, or a and b, from our interval. So when we do that, we plug in 10 first, and then we subtract 0 when it's plugged in. So we get 1 over 200 times the quantity of 3 times 10 plus 1/3 times 10 cubed minus all of this turns out to be 0 because 3 times 0 is 0 and 0 cubed times 1/3 is 0. So we're just subtracting 0. So we end up getting 1 over 200 times the quantity of 30 plus 1000 over 3. And this ends up simplifying down to 109 over 60. So now for part B, we need to find the volume of the funnel. So let's go back up to the equation. We can think of this as a normal volume problem, a normal volume rotational problem. So our original area, as I have drawn here, can be, let's see, it can be this area right here. We have that shaded in. And then it's rotated around this center line, the axis. And then we have our cross section drawn here, which is a solid circle. And we are going to be using the area of a circle, pi r squared, and our radius is the equation given to us down here, and that's r equals 1 over 20 times quantity 3 plus h squared. So what we need to do is take the integral of that to find the volume. So we get volume equals the integral from 0 to 10 of pi times our radius equation, 1 over 20 times quantity 3 plus h squared, and all of that is squared, dh. Let's go ahead and factor out the pi. Again, it's a constant, so it'll make it easier to simplify. And then we're also going to factor out this 400 here, because again, a constant, making it easier for us. And look at this nice polynomial we get to integrate. So when we integrate, we get pi over 400 times the quantity of 9h plus 2h cubed plus 1/5 h to the 5th on the interval 0 to 10. So again, we plug in the 10 value, so we get pi over 400 times the quantity of 9 times 10 plus 2 times 10 cubed plus 1/5 times 10 to the 5th minus 0, because when you plug in 0, again, this all just becomes 0. And then you multiply it out, you simplify, and it all comes down to 2,209 pi over 40 inches cubed. It is a volume problem, so we do need units, especially because we are given the units here as r and h are inches. So now for the final part, part C, the funnel contains liquid that is draining from the bottom, so we know that this is going to be a negative rate. At the instant when the height of the liquid is h equals 3 inches, the radius of the surface of the liquid is decreasing at a rate of negative 1/5 inch per second. So we know that this is dr dt, the rate of change of our radius, and we know it's negative because it's decreasing, so dr dt equals negative 1/5 inches per second. At this instant, what is the rate of change of the height of the liquid with respect to time? So what is the rate of change? We know that that's what we need. So we are solving for dH dt. So if we come over here, this is just our typical rate of change problem. So we want to list what we know and what we want. So we know h equals 3. Because we have h, we can also find r because we have the equation for r, and that's in terms of h. So we just plug in 3 and we get 3/5 as a radius when h equals 3. And dr dt equals -1/5 inches per second. And we want to know dH dt when h equals 3. So now we are going to use the radius equation. So radius equals 1/20 times the quantity of 3 plus h squared. And now we want to derive this. So we get dr dt equals 1/20 times 0, because 3 is a constant, derivative of a constant is 0, plus 2h dh over dt. When you have a variable here with a multiplicity, you need to multiply by dH dt, because that is the derivative of h. So now we can plug in what we know. So we get -1/5 for dr dt equals 1/2 times 3 dH dt. And then we get all this to simplify down. We get dH dt alone, and we get it to equal -2/3 inches per second. And this is the rate at which the height is changing, because it's negative when t equals 3 seconds. So what are some common mistakes? Well, first off, integration and deriving is key. If you don't know how to integrate or derive correctly for all of these problems, you will get very few, if any, points for this FRQ. Also, when finding the volume and when the cross section is a circle, don't forget to multiply by pi and square the radius. I know I forget to do this a lot, so like for this part B, don't forget to put your pi out in front or inside, whichever you prefer, and square the radius. Now, if your cross section happens to be a disk, if there was another circle on the inside of this and you had 2 different radii, then you would need to square each of these separately. So you do the big R squared, you get big R squared minus the little r squared in the integral from a to b times pi times dt, I believe. th, whatever your variable is. Another common mistake is making sure you derive the correct equation. When you're dealing with rates of change problems, I know I always struggled with knowing which equation to derive. This one's fairly straightforward, being the radius and having all the variables in it that you need, but just make sure you pay attention to that and make sure it's the right one which you are deriving. Also, do not plug in values before you derive. Otherwise, if I were to plug in before I took the derivative, I would get a big constant, and the derivative of that is just 0. That is not the correct answer. That's not the answer we want. So only plug in values after you take the derivative. And finally, remember units. If your problem has given you units like this problem has with r and h in inches, or if it's solving for the volume or the area, make sure you use units, because yeah, you need units. For more practice with these types of problems, you can check out these couple of sites. So for related rates, you can go to slideshare.net, just search related rates FRQ, and it's the first result that comes up. It includes several AP FRQs on related rates, plus the work shown. It's all worked out very neatly, more like how you would see it instead of with the AP style. And with the same website, they do the same with rotational volumes as well. Also, if you want to see more just all types of FRQs, you can go to daringmath.com. They have a ton of FRQs and they're organized by topic. All right, thanks for watching. I hope this helped you understand the solutions for 2016's AP FRQ number 5.